back to stats. And actually, one of my favorite topics in forecasting, which is, if you guys will figure this out, I love thinking about uncertainty. I kind of obsess over uncertainty. I kind of alluded to in my intro slides that, like, with uncertainty propagation being like a key part of that Clark definition. So what I want to talk about this afternoon are some key concepts, but I'm going to focus in particular on this uncertainty propagation. But hopefully, like, how these things relate to each other is pretty clear. So I'm going to start by talking about the sensitivity analyses, which basically ask the question, how does a change in some X translate into change in some Y? And then move from there onto uncertainty propagation, which is basically the question of how do we forecast Y with uncertainty is actually turns out to be very closely related to the question of how does the uncertainty in some X affect the uncertainty in Y, and thus relates back to that sensitivity question, because now we're, instead of talking about a change in X, we're talking about the uncertainty and a change in Y, the uncertainty in Y. Once we understand how to propagate uncertainty, it's useful to think about how to actually analyze those uncertainties to understand which of them are important and to partition them out. And then thinking about how we can use that information to kind of come full circle to questions about how do we better design our monitoring programs and our experiments and our sensors and stuff like that based on understanding the uncertainties in our forecasts. And if you understand what which uncertainties dominate your forecast, you know on a very practical level where to put your effort into collecting new data. Okay, so sensitivity method, this is going to be a quick and dirty review. You can kind of divide sensitivity analysis methods into local versus global. Local ones can be done analytically. If you have a model that you can take derivatives of, df d theta is sensitivity. You can also do these using basic one at a time perturbations, just wiggle each parameter around. So this is an example of specific leaf area, which is basically the ratio of the area of a leaf to its weight. And it affects, in this case, I think the y-axis was net primary productivity and exploring the range of variability. One thing that I always recommend when it comes to sensitivity analyses and interpreting them, a lot of earlier text I read when I was a graduate student was always like plus or minus 10%, plus or minus 20%. I think it's much more useful to be like plus or minus 1 standard deviation, plus or minus 2 standard deviations, because then the amount of variability that you're changing a parameter on is somehow meaningful. Because some parameters plus or minus 1%, and some of them plus or minus 100%. Global sensitivity analyses try to explore changes in multiple parameters simultaneously and face the basic challenge of any time you're exploring parameter space is that how parameter space goes up exponentially with the number of parameters in a model. So if I go from doing a one at a time analysis to 2 things at a time to 3 variables at a time to 4 or 5, it grows very quickly, which is a persistent challenge, not just for sensitivity analysis, but for any sort of calibration, how big parameter space can get. There's a whole range of global sensitivity analyses, and I highly recommend the Saltelli book, which I think if you poke around a little bit on the internet, you can find a PDF version of this for free pretty easily, because it covers a wide range of different sensitivity analysis methods. This is just a subset. But they basically involve a set of trade-offs between approaches that are very clever in how they explore parameter space in order to minimize the number of times you have to run your model, to those that explore parameter space much more extensively, but that comes at the cost of much more compute. One thing I will point out, though, is if you rely on Monte Carlo approaches for how you calibrate your model, or Monte Carlo approaches for how you propagate uncertainty, which we'll talk about later, that you sometimes can get some of these sensitivity analyses for free. So this is an example of, it's actually a Gaussian plume model that predicts how atmospheric pollutants, the concentration of them, change as a function of other atmospheric variables, in this case wind speed and atmospheric pressure. And I'm just, I'm varying all the variables simultaneously, and I'm just kind of plotting, how does the y that I'm interested in change as a function of all the, hundreds of thousands of times that I've run this model. And just, things like, just fitting an empirical regression slope gives you an estimate of sensitivity. Fitting just the r squared of that gives you an estimate of the relative importance of that variable. How much of, so if a variable explains 17% versus less than 1, this one is clearly more important. Not just because its slope is steeper. Cool. So that was all I wanted to say about sensitivity analysis. Mostly a reminder of a concept that I hope is one that many of you have heard of before. So then wanted to kind of dive into this question of if I have an estimate of the uncertainty in my system right now, and I want to propagate that into the future so that I have a probabilistic forecast, how do you actually do that? So making this idea that you have some distribution of uncertainties in your inputs, some function that describes the relation between your inputs and your outputs, and you want to translate this uncertainty into that uncertainty. And it's unfortunately it's more complicated than just plugging in the mean and plugging in the standard deviation. You can't just you can't just put the variance into your function and expect to get the variance back out. But there's a bunch of different ways that you can do uncertainty propagation, and I actually think it's, in the concept of thinking about forecasting, worth understanding what these different approaches are and some of the trade-offs among them. They also had this I was amazed at the depth of XKCD and obscurity when they actually had an XKCD on error propagation, which came out years after I wrote my book, so it's not in the book. I was very disappointed. But I love the idea of just recursively putting error bars on all your error bars on your error bars. That's not how it works. So in thinking about uncertainty propagation, I'm going to divide this into these kind of 4 quadrants. So first, we're going to think about the distinction between analytical approaches for uncertainty propagation, which is where you have to do math, versus numerical approaches to uncertainty propagation, which is where you have to write code. And then on the other dimension, I'm going to think about, what do you want to get out of this? Do you want to get the full probability distribution out, or is it sufficient to just get some statistical moments? So if all you care about is the mean and standard deviation, you don't need the full distribution. So in general, things that just give you moments, such as mean and standard deviation, are easier and cheaper than things that give you the full distribution. And then obviously the trade-off between having to write code versus having to do math is one that you can weigh based on your personal, depending on which of these things you hate the most at the moment. Some days you hate code and some days you hate calculus. But I would say the gold standard that I'm going to start with is this idea of a variable transform. So if you know the probability distribution of your input, you want the probability distribution of your output, which you can't just like take a normal distribution and drop it in to if I have some function of x, I can't just write down, oh, I want to write the function of the normal distribution of that doesn't work. What you end up having to do is this ugly bit of math where instead of plugging the function instead of dropping the distribution into the function, you drop the function, the inverse of the function, into the distribution. And then you also have to take the derivative of the inverse of that function. If you think that's ugly, realize that most models have more than one parameter. So if you have more than one parameter, this is a complex multivariate function. This is a multivariate distribution. And this becomes a Jacobian matrix of all derivatives of all inputs versus all parameters. It gets ugly incredibly fast. So I would say this is the gold standard that you will see in this slide, and if you're lucky, you will never, ever have to do. So what if you do in practice? Well, analytically, that math is hard because it involves derivatives and inverses and functions. So I said that, well, the alternative is, what if I'm just interested in statistical moments? Turns out there's this, I'll call these the analytical moments methods of thinking about kind of what you might call the algebra of how different moments work. So the algebra of kind of how means work is fairly intuitive. The algebra of how variances work is a little bit less intuitive, but there's a whole set of rules that you can apply to functions to understand how to actually kind of do this math. So like if I have, if I want to know the variance of some constant times some random variable x, that's just that constant squared times the variance of x. The variance of a random variable plus a constant is just the variance of that random variable, because constants don't have variance, and so on and so forth. And so there's a whole set of rules that you can apply. If you can write down your model, you can apply these sorts of rules to say, what would the variance of that model be? And you can do the same thing for the means. And you can look up these rules in the back of many stats textbooks. You can look them up on Google, Wikipedia, places like that. Now, the challenge is that the exact analytical solutions for playing with this only work if your model is linear and additive. So if your model's a regression, this works. But if your model's a regression, someone else has already figured out all the math. So, so what do you do? Okay, I want to talk about the relationship between this, and I'll talk about what do you do when the model is a straight line. So you have some linear additive model, y equals m theta plus b, because I'm going to do theta as my x-axis. M is a slope. Slopes are derivatives, so that's that kind of relationship between that and sensitivity. I have some input distribution, and I can analytically transform that to get the variance of that output distribution. And I just, to kind of show how I applied these rules. So I want the variance of y, that's the variance of this function, and then I can just apply those rules. The variance of, remember, the variance of constant is going to be 0. Constant times random variable is going to be that constant squared. Boom. And we have an analytical solution, which is also kind of showing us that the output, and this concept here is one that we'll come back to a lot in this lecture. This idea that the uncertainty of an output, I actually said this on Monday as well. The uncertainty in the output is determined by the uncertainty in the input and the square of the sensitivity of the output to that input. I said it on Monday, but now I've actually kind of walked through the math of why that's true. So what if your model isn't a straight line? To apply this kind of approach, the standard approach, I've given it away, it's on the top side, is to take a linear tangent approximation of your model. So if I want to translate the model, I can't translate the uncertainties through the squiggly line, so I'm going to translate it through this dashed line, and the extent to which, whether that's a good thing to do or not, depends on how nonlinear that function is, as well as how uncertain your inputs are. So if the variance of this was very large, then this is a really bad approximation. But if the uncertainty in this was very narrow, and I'm just doing the translation around there, it might be a fine approximation. But the basic idea is you're doing the uncertainty translation around the linear tangent approximation. And so now, instead of the variance being exactly dy d theta squared variance of theta, it's approximately, because we are taking an approximation of that nonlinear function. Applied more generally to any kind of function in general, the variance of some function is approximately the variance of the Taylor series expansion of that function, which works out to be the same thing that we've seen before. And that actually works out that way because the variance of a constant is going to be constant. This is also going to be a constant that's going to be constant. So you're going to end up with this f theta as the only things that aren't constants. In theory, you can move this on to higher moments as well. In practice, the math gets ugly really quickly. And yeah. Now, actually I'll jump back. One of the rules I glossed over that is actually kind of important here is the variances of combining random variables. So if I have two random variables, x and y, the variance of that is the variance of one, the variance of other, and 2 times their covariance. And then if I have constants, I have, the constant squared variance one, constant squared variance the other, 2 times the product of those constants and the covariances. So if I want to generalize what I was doing here to a multivariate sense, I have, the sum of each of the individual terms, variance of each thing, sensitivity of each thing, and then I also have all of these covariances between the two things and the product of their individual sensitivities. And in fact, you don't actually even need these as separate terms, because really the covariance between I and I, the covariance between theta I and theta I is the variance. And, f of theta I times f of theta I is just f of theta I squared. So it's really just this, summing over all terms. And actually the 2 shows up because you have the variance of itself twice. Cool. And this is actually where this equation that I showed yesterday came from, by taking the linear tangent approximation to kind of the generic forecasting model. We had this kind of partitioning of uncertainties that we talked about yesterday in terms of how we think about the predictability of different forecasts. You also note that the thing I showed you yesterday dropped that covariance term. And that covariance term was dropped for the sake of conceptual explanation, but it's important to acknowledge there. And I think it's going to be very important if you want to think conceptually about how forecasts scale in space and time, that the strength, if I'm making forecasts at say two spatial locations, and I'm trying to understand, maybe aggregating up in space or aggregating up in time, that the strength of those covariances will have a big impact on how quickly things become more predictable as you scale up in space and time. So if all your forecasts are independent, there's no covariance between them, as you move up in space, they should become more predictable, because a lot of the random errors should cancel out. But if there's a large spatial covariance, then that's not going to average out quickly. Okay, so now we've talked about these analytical approaches to uncertainty propagation, and they have the obvious disadvantage that they require you to do math. They give you, but I do think even if you never do the math, they give you a nice conceptual understanding of what's going on. So even if you don't apply this to any actual model, I think it's a good conceptual understanding of what's going on under the hood. In terms of how we actually do this the majority of time in forecasts, is we do end up using numerical methods, and we rely on what are either called ensemble methods or Monte Carlo methods. And the distinction between ensemble methods and Monte Carlo methods is kind of a murky one in the literature. The way that I tend to think about it is, if you are like when we did MCMC, we ended up taking thousands of samples of our parameter sets. We took so many samples of our parameter sets that we could approximate the full distribution from those samples. So that's kind of what we think about when we talk about doing Monte Carlo approaches, taking enough samples that you can approximate the distribution itself with those samples. Colloquially, the word ensemble is usually used in a sense when you're working with a much smaller number of samples. So, the CMIP might have 20 Earth system models in it. And that's how we understand future climate change. We're not running an ensemble with 5,000 different climate models. So we don't actually have probabilistic predictions. But on the flip side, how many data points do I need to get a decent estimate of a mean and a variance? 20, 30? So with small sample sizes, you can get reasonable estimates of your mean and variance, but you can't approximate the full distribution. And so usually in practice, the distinction between these has to do with your computational resources and the speed of your model. If you have a model that's lightning fast, there's really no argument for running it 20 times. Run it 5,000 times. Don't be lazy. You get the full distribution and all the things you would want. If you have a model that's going to take a week to run, you're now talking about doing either ensemble-based or resorting to some sort of analytical approach. But the basic idea, and this is how a lot of forecasts happen in real life. So this is an example of a numerical weather forecast that shows this kind of chaotic divergence of weather forecasts, but it shows that in practice, operational weather centers these days rely on ensemble-based methods. They used to rely on linear tangent-based methods. Turns out maintaining a linear tangent version of your Earth system model is a pain in the butt when it's million line of Fortran code. They ultimately realized that the computational cost of running the model 31 times a day was easier than doing the analytical version. So one of the things I like about the analytical approach, though, is it helps us address a real challenge we have whenever we want to do uncertainty transforms through nonlinear functions, and which is basically the Jensen's inequality will rear its ugly head a lot, and most of the mistakes, well, not all, most, a lot of the mistakes I see with uncertainty propagation come from people that fail to stop and understand Jensen's inequality, which in its simplest form just says that the mean of a function is not the function of the mean. So why does that matter? Because the most common thing I see people do is to take the mean of some input into their model, whether it's the mean parameter estimate, or the mean initial condition, the mean weather, and plug that in and run their model once under the mean conditions. So they put the mean as the inputs in the function. There's no guarantee that that's going to give you the mean of the prediction. Because this is what you actually want, the mean of your forecast, not the forecast under your mean. To give a simple example of like why Jensen's equality matters, or that it exists and it's a very real thing. So imagine I had just a simple standard Gaussian, this is just a normal mean 0 standard deviation 1. Simplest problem. It's a normal 0, 1. And I want to transform that to an incredibly simple model, x squared. Okay, mean is 0. 0 squared is 0. Every single value is positive. Can the mean be 0? No. The mean of a function is not the function of the mean. If you plug in, you will get biased predictions. The mean's actually 1. And I can do this, and you can, if you do this through brute force simulation, sample this, 10,000 times, square every sample, you will get the right answer. So one of the beautiful things about ensemble and Monte Carlo based approaches is that we can't push statistical moments through functions, but we can push samples through functions and we get samples out. So ensemble based approaches handle transforms as nonlinear as can be, and they give you correct samples out on the back end. And they do it in a way that didn't require you doing any math. They just require, anytime you can take samples of your inputs and run them through, you get samples of your outputs. Worth noting that if you go through the math of the, what did I call it? The one that I said was the gold standard. The variable transform. If you go through this math, where this function, is x squared and this function is the normal, and you get out, does anyone know? Because I think this is either the dumbest or I'm still torn on whether this is the best or worst named distribution ever. Chi-squared. So it's, like I said, it's either the best or worst named distribution ever. Because it's, if you ever wonder what the chi-squared distribution is, it is the x-squared distribution. That's where it came from. Someone just made a connection. That's what that is, yes. And that's why chi-squareds end up describing variances all the time, because you're squaring, yeah. Okay, so how do you do this in practice? It is an incredibly simple algorithm. You set up a loop, or if you're being really clever these days, you do something in parallel. You draw random values from the input distributions, you run your model, you save your results. As long as you can run your model lots of times, and then you summarize that in terms of some set of distributions. So it has a simple example. I'm just going to take a regression model, and I'm going to take a sample from the slope and intercept from that regression model. And an important thing is I have to take a sample from that joint distribution. So I don't sample the slope and sample the intercept independently. I sample them jointly because otherwise I lose the covariance between them. And this will just show a simple animation of doing that sampling. And so each of these are ensemble members. They're ensemble predictions of the uncertainty in a linear regression. It's kind of small now, but it's starting to look like a regression confidence interval. And the cool thing is, at any particular value of x, if I go up and take those samples, I now have a histogram of predictions. Another thing that's worth noting, because I love talking about uncertainty and I love harping on covariances, each prediction is a line. So you always want to treat all those values on a line as being related to each other. So that if you do that, you will always capture the covariances correctly. So if I wanted to know, like, if I made a prediction here and a prediction there, and I wanted to know the covariance between those two predictions, I want to keep track of like where which line each one came from, because then I could actually calculate how those two are correlated to each other, because they are, because they're lines. And that's going to be true when you think about time series forecasts as well. The ensemble of forecasts is the collection of all the time series themselves. Or like I talked about state space models before lunch, the MCMC draws are draws of time series, not draws at each point. And if you do this with spatial stats, your draws are maps, not individual things. So you get the uncertainty propagation, but you always have to treat a line, a time series, a map as a sample itself to get the covariance right. Why do I care about covariances? There's a great story in oh shoot, Nate Silver's book on forecasting, the guy that does 538, does all the election forecasting and sports forecasting, is a blog. I forget the name of the book at this point. But he makes this really interesting argument in the beginning of the book about how failing to account for covariances caused the global economic collapse of 2008. And his argument is that the economic analysts that were doing assessments on the housing market, because it was the mortgages that caused a lot of that collapse, treated the risk at each mortgage independently. And if you have enough independent mortgages, the uncertainties, they average out and you get a very predictable response. But what if those events aren't independent? What if they're highly correlated? Now the uncertainty averages out much less slowly. And well, that's what happened. And so mortgages, the collapse of individual mortgages wasn't driven by individual level misfortune. It was driven by macroeconomic patterns, and suddenly whole regions were defaulting on mortgages simultaneously because of covariances. So covariance structure, you can collapse the global economy, which also is my argument whenever I get pushback about like the uncertainty in climate models and their economic inputs. They're like, economists have collapsed the global economy multiple times over bad forecasts. How bad could we do? Like, yeah. Anyway, so the ensemble version of this is very similar, but the key, like I said, the key difference is that in the ensemble version, the n is much smaller, and that when you get your outputs, you have to make some sort of distributional assumption. So with Monte Carlo, you have enough samples that you can just use the samples. When you have a small ensemble, you have to fit those outputs to some distribution. Very often you assume it's normal and you just calculate the mean and standard deviation and calculate your intervals by 1.96 standard deviations and stuff like that. Worth checking that your distributions are normal, but yeah, pretty standard practice. Also worth noting, as I said here, when you talk about drawing random values from distributions, if your parameters came from MCMC, you already have that. So like Monte Carlo, MCMC and Monte Carlo error propagation go together very nicely. And so the trade-off there is between sample size and your willingness to make assumptions about distributions. And this is kind of just comparing a few different things. So like a Monte Carlo approach to transforming some bivariate distribution through some crazy function, the Taylor series analytical approximation to that, and then there's some cool tricks out there in the literature for dimension reduction when you're dealing with really computationally challenging models. Yeah, the unsunded transform is about a dimension reduction approach that instead of picking your ensemble members randomly, picks them very systematically. But most of us don't deal with models that we have to deal with our sample sizes that small. Cool. So the next thing I wanted to note was that there is a deep connection between these different flavors of uncertainty propagation and the different approaches to data assimilation that exist in the literature. And remember, data assimilation is that idea of iteratively updating our forecasts as new data becomes available. So if you propagate your uncertainty analytically, you will end up using a data assimilation approach called the Kalman filter. If you use the Taylor series, you end up using the extended Kalman filter. If you propagate your uncertainty using an ensemble, use the cleverly named ensemble Kalman filter. And then there's this thing called a particle filter that deals with, when you are doing your uncertainty propagation using a large Monte Carlo ensemble, and yeah. So I just want to very quickly kind of walk through that relationship between uncertainty propagation and data assimilation in this iterative updating, kind of reminding you this idea that we want to propagate our uncertainty, but that we want to update that information is update when new information becomes available. So I'll do this by walking through what I would argue the simplest variant of data assimilation. So let's imagine our forecast has some normal distribution with some mean UF, F for forecast, and precision PF. Well, I think it's a variance. I think I actually wrote this down in a variance context. Variance PF, again, little f for forecast. The mu f and pf come from, like I said, if you use analytical moments, mu f and pf comes from that. If you use a Taylor series to do uncertainty, mu f and pf come from that. If you use an ensemble to propagate your uncertainty, mu f and pf just come from the ensemble mean and variance. So you now know all you need to know about data assimilation. We have some observation error. We assume that to be Gaussian. So that's our likelihood. If we assume that the data and the forecast and the observation error are known, then our analysis, our updated understanding of the system will itself be Gaussian, because we have a Gaussian times a Gaussian. Remember, we went through yesterday that a Gaussian prior times a Gaussian likelihood gives you a Gaussian posterior. And we actually went through the math as well. This was all foreshadowing. We went through the math and we saw that if we convert those variances into precisions, that our analysis is a weighted average of our forecast and our likelihood, each weighted by their precisions, and the updated analysis precision is the sum of the forecast and likelihoods precisions. There's a reason I went through that example. Cool. So that in a nutshell, and that in a nutshell is the Kalman filter. If you look it up, you'll see that this is usually derived in a multivariate sense with a multivariate normal, and all of this just becomes expressed in matrix form and looks ugly because matrix notation for something like this just looks scary. But it's basically the same thing. It's just a weighted average between the forecast and the data, each weighted by its uncertainties. And like I said, the key difference is just how you do the different uncertainty propagation to get the forecast mean and uncertainty, and then we assume, yeah, we do this. Cool. I'm gonna pause at this point and ask if there's any questions about, particularly about uncertainty propagation. Yep. Yes. Yes. So when your model is linear and additive, then it's like I showed before with the analytical moments. When your model is linear and additive, it all works out, and there's no issues there. It's really the non-linearity of any function that causes the issue. I'm willing to bet most of you end up making forecasts that involve some sort of non-linearity. Cool. Okay, so I wanted to next kind of talk a bit about, now that we've talked about the sensitivity, we've talked about uncertainty propagation and how that's related to the uncertainty and the sensitivity. I then want to talk about how we can use those ideas to pick apart or partition out those different uncertainties. And this is kind of reinforces what I was saying earlier, that if we think about our predictive uncertainty and how different parts of our model may contribute to that, that's determined both by the uncertainty in the inputs and the sensitivity to them. So the worst case is if you have a very uncertain input and you are highly sensitive to it, you end up with a very uncertain output. On the flip side, if you have low uncertainty in your input and you're not very sensitive to that input, you end up with very little uncertainty in your prediction. But it's worth noting these two other cases also matter, that something can be important either because it's uncertain or because it's sensitive. I point that out because in my mind, it illustrates that um, that sensitivity by itself is not sufficient to understanding what's important in your prediction, and it can often be misleading. I've seen lots of examples of people fixating on highly sensitive parameters in models that are actually highly constrained and thus don't actually contribute very much uncertainty to predictions at all. I've also seen them ignore parameters as insensitive that are really poorly constrained and actually do matter. Likewise, you can't just look at the uncertainty in the inputs, because you could have some input that's highly uncertain but completely insensitive. So again, it's that combination of sensitivity and uncertainty. So this is an example that takes that idea we had before, that the overall, actually, I've been told that you can't see that well. Did that one come down? All these boards, and I'm losing track of which one I want. Yeah, here's a clean one. So if we do our uncertainty propagation analytically, the uncertainty partitioning is kind of already there, because if we're summing up all those terms, we're literally just summing them up. The uncertainty contribution is those individual products for each term, and they add up the overall uncertainty. So this is an example of a variance decomposition that we've did on one of our carbon cycle models, where I look at this. So here are a bunch of different parameters that affect vegetation. Here's this overall, these partial variances for each of those model parameters. And then these two things, elasticity. So, CV is just, the variance, or is it standard deviation? I think it's the standard deviation divided by the mean. So just, it's basically this uncertainty term normalized to get rid of the units. And then similarly, dy y bar d theta bar also just gets rid of the units. So this, what I'm calling CV and elasticity here, are just versions of the sensitivity in the parameter uncertainty. I had that backwards. Parameter uncertainty, sensitivity, normalized to get rid of units, just so I can visualize them. And you can see examples of like the leaf turnover rate and the specific leaf area have these very similar contributions to the overall uncertainty, but one's an example of a parameter that is highly sensitive but fairly well constrained, while the other one is poorly constrained but not particularly sensitive. They have almost the exact same contribution to the overall uncertainty. Here's a question for that specific pair, leaf turnover rate and specific leaf area. If I want to reduce the uncertainty in this model, which one should I target for further field research? And why? Who'd want to go out and collect more data on leaf turnover rate, the thing that is uncertain, high uncertainty but low sensitivity? A couple of you. Who wants to go and get more data on specific leaf area, the thing that is low uncertainty but high sensitivity? Okay, I'm going to argue in favor of leaf turnover rate, because if you think about uncertainty, uncertainty tends to decline asymptotically as sample size increases. For something like a simple, mean estimator, this is your classic, 1 over square root of n sort of problem. So I would argue that leaf turnover rate is here, and SLA is here. If I double this sample size, I get a much greater reduction in uncertainty than if I do this, similar increase in sample size, because I'm in the point of diminishing returns here. If something's highly sensitive but already highly constrained, you're going to need a lot more data to reduce its uncertainty further. You get a lot of bang for your buck for things that are highly uncertain and just happen, but also not highly sensitive. It really wouldn't take much. And a great example of that, I didn't say that one thing that we're showing here in the gray versus the black is the difference between doing this on the priors versus the posteriors. And so everything where the gray and the black are different, or where we actually had field data that we could add. And this model slope is my favorite example here, because not that it wasn't the most important thing in the prior, but I think it was like 6th most important. But when I did this analysis, I was still at the University of Illinois, and the guy down the hall from me, Andy Leakey, is probably one of the best ecophysiologists in the world for understanding stomata sensitivity. Andy sent a grad student out and in one weekend collected enough data to turn this into a completely insensitive parameter, because we knew what we needed to target and we knew how to target it, and reduced its uncertainty considerably, and it's now one of the least important things in the model. But that was an example where it was never highly sensitive as much as it was just not well constrained yet. And then this is an example of doing this kind of at the, actually I need to update this. This Thomas one is now published. Kind of looking at not just this in terms of individual parameters, but in terms of these larger sets of things. So, we talked about earlier how process error, parameter error, initial condition uncertainty, driver uncertainty, how those things at a high level contribute to the uncertainty in our forecast. And so here's kind of comparing, one of Quinn's aquatic forecasts to one of my terrestrial ecosystem forecasts, and kind of thinking about the relative contributions of different things. In both cases, our initial condition uncertainty drops off exponentially, because we talked about yesterday, that feedback loop, if that sensitivity is less than 1, that feedback drops exponentially. Differences in parameter uncertainty, both showing that the relative importance of driver uncertainty increases through time. That's a general pattern, because this is actually an important point worth making. Anything you forecast, you need to be able to forecast all the covariates that you put into that model. So if you want to predict, if I want to predict vegetation productivity in the future, and my proxy for vegetation productivity is NDVI, and no one's made an NDVI forecast, good luck, because you now critically depend on a X that you don't have to put in as a predictor. But since we have to predict all of our covariates, and anything we predict becomes more uncertain into the future, the uncertainty of our covariates will also increase as we go into the future. That's a general pattern. So thinking about this a little bit more formally, and I'll wrap up after this, we can use this partitioning of uncertainty in a more formal way to think about, kind of in a power analysis sense, what sample sizes do we need to reduce our forecast uncertainty by a specific amount, and then kind of this observational design level, what do I need to measure? Where do I need to measure it? How do I gain that information most effectively? So like I said earlier, we have this general pattern that uncertainty in our parameters are going to decline as a function of sample size. And we have this idea of power, where we want to manage our false positives and our false negatives. So power is going to be a function of effect size in our standard error. And for simple models, you can do those sorts of power estimates analytically, or there's lots of functions in R for a lot of classical models to do power. But you can also do these through basic pseudodata simulation, which is very similar to what we just talked about with the Monte Carlo propagation. It's very similar to if you've heard of bootstrapping, but the basic idea being you draw a random, you simulate pseudodata of some sample size that's bigger than what you have already. You fit the model to that simulated data and you save those estimates, and you repeat that a bunch of times to get an estimate of how the uncertainty is going to decrease as a function of sample size for your actual model, rather than something as simple as fitting a mean. And so you can kind of repeat this. You can start off with your current parameter estimates and your current sample size, and then ask what if I doubled my sample size? What if I quadrupled my sample size? How much uncertainty do I think I can get as I increase my sample size? And depending on how you do this, you're either resampling the data or simulating the data from your process model. So that tells you how the individual parameters in your model are going to decrease as a function of sample size. What you can then do is come back to this uncertainty propagation step and then ask, how do I translate the uncertainty in those model parameters and how they're declining with sample size into how the uncertainty in my prediction will change as a function of sample size? Because I'm just doing that propagation from the parameter uncertainty into the predictive uncertainty. And one thing that's nice there is if I'm looking at individual parameters, each parameter in my model is going to have different units. But if I translate that into model predictive uncertainty, they all have the same units, the units of the thing I'm predicting. So here's an example where I have two variables, variable 1 and variable 2, and translated them into how the uncertainty is likely to reduce as we further increase the sample size for each. Which would you prefer to measure? 1 or 2? If I said you had to go out and measure one of these things, variable 1 or variable 2, to reduce your forecast uncertainty, which would you measure first? 2. It's not a trick question. 2 goes down more quickly. But the trick question is, would you keep measuring 2? And you wouldn't. So here's an analysis that then combines those two in terms of just a basic economic concept, marginal cost, marginal benefit. So if I keep sampling variable 2, at some point, and it's about 7 data points in, the marginal reduction of uncertainty from going and measuring variable 1 is greater than the marginal, because this one will start to level off. And at that point, that becomes steeper. So you actually get this kind of switching behavior. So for any given sample size you're willing to invest in, it would tell you you could think about not just what you should measure, but the relative balance between different things that you need to measure. But the other trick question there is, but is it as easy to measure variable 1 as variable 2? And so here's an example where I ascribe different costs, marginal costs, to each of those different measurements, and you get a very different sampling protocol depending on what the marginal costs of different things are. The other thing that I don't show here is you can also not just think about the marginal cost of sampling, but also the fixed costs. Instrumentation has to be bought. Plots need to be set up. And it actually reaches the interesting conclusion that like 2 labs may come up with very different optimal sampling designs depending on what toys they already own. And that your sampling plan can change enormously once you reach a budget level that allows you to buy a different toy. But these are the sorts of things you can actually do by combining an understanding of the uncertainty in our forecast with some basic Monte Carlo simulations of how those uncertainties would change, which I think are just kind of really powerful concepts. And to kind of taking this to this next level is this idea of what's, this is an idea that's very common in the Earth system sciences, but I find remarkably absent in my conversations with epidemiologists, which is the idea of the observing system simulation experiment, which is the idea that you use your best process-based model of how the system works to simulate how you think the true system behaves. You then simulate pseudo-observations from that system, and then you assimilate those pseudo-observations and assess the impacts. It's basically what I was showing before, kind of a Monte Carlo bootstrapping sort of power analysis on steroids, where you're now, if NASA wants to deploy a new satellite, if NOAA wants to deploy a new global network of buoys, like they do this on a global scale. And what they do is they simulate observations under different sensor designs, under different spatial arrangements of sensor networks, different sample sizes. Like you can do this really at scale, and the Earth system sciences, physical Earth system scientists folks do this at scale. Propose different engineering specs on a sensor and ask how would that assess our ability to improve our weather forecast. And if I design the sensor a different way, does that improve? Is that give us more or less information? So you can do it for new sensors, additional locations, etc. And I think, yeah, I'm not an epidemiologist myself, but the folks that I talk to at least at BU where I am say that people are not doing public health observation this way yet. I think it's a missed opportunity. Now here's just an example paper kind of going through this idea. It's often abbreviated to the acronym OSI, which is a fun acronym. Cool. I think that's all I had. I actually finished right on time.